In this video lecture, we construct a Fourier trigonometric approximation for the function f of x equals x plus 1 on the interval from -1 to 1 up to capital N equals 5. After finding the approximation, we sketch the graph of f against its Fourier approximation. For the final part of this video lecture, we find the general formula for the different coefficients of the Fourier trigonometric series. If the Fourier series of f is given by c sub 0 times phi sub 0 plus c sub 1 times phi sub 1 plus c sub 2 times phi sub 2, and so on, where the phi sub n's are the basis functions, then c sub n is given by this fraction. The numerator is the inner product of f with phi sub n with respect to omega over the interval from a to b. The denominator is the inner product of phi sub n with itself. The kind of Fourier approximation determines the type of basis functions that we are to use. A basis is simply a set of vectors, or in this case, a set of functions that we use to construct an object. In this lecture, the object that we are to construct is a Fourier trigonometric approximation. Since we are to construct a Fourier trigonometric approximation, the phi sub n's, which are the basis functions, will be made up of cosines and sines. And so we split up the approximation into cosine and sine terms. For a Fourier trigonometric approximation over the interval from -L to L, we have f of x is approximately equal to a sub 0 plus a sub 1 times cosine pi x over L plus a sub 2 times cosine 2 pi x over L, and so on. And since we are to go up to capital N equals 5, we have plus a sub 5 cosine 5 pi x over L. We have a similar set of terms for the sine terms. Since the interval is from -1 to 1, we replace L by 1, and we get a simplified version of the approximation. We will find the different values of a sub 0 all through b sub 5 using Mathematica. In this case, we will employ a very basic Mathematica code to do the calculations. To get started with the Mathematica code, we first define our function. Note the underscore after the variable x to indicate that we are defining the function. We use the underscore only when we define the function. After this definition, we do not need the underscore. Then we define omega. Instead of the Greek letter omega, we use w. So we have w of x. Again, we need the underscore because we are defining the function. Omega of x, or w of x, is equal to 1. We next define L. Capital L is equal to 1. Next, we type the lines to calculate the different a sub n's for the cosine functions. For this, we will use a do loop. We have a bracket n to indicate a sub n, where we store the value that we get by using the built-in Mathematica command integrate. What do we integrate? We integrate f of x times the corresponding phi sub n. In this case, it is cosine n times pi times x over capital L. And then we have omega of x, or w of x. We integrate from -L to L. Now this is the numerator for a sub n. The denominator is the integral of phi sub n squared times omega. Phi sub n is cosine n times pi times x over capital L, multiplied to itself, and then times w of x. Again, we integrate from -L to L. The do loop is very useful if we are calculating one object. Now in this case, we're calculating a sub n, and the only thing that we change in the formula is the index. The index is n, In this case, n goes from 0 all the way through 5. We evaluate all the commands. We press Shift-Enter. Well, nothing happens. We do not see the a sub n values because we need to tell the software to show us the a sub n values after the software has calculated what they are. For this, we use the built-in command table. So we have the table of the a sub n's. N goes from 0 through 5. We press Shift-Enter again to evaluate, and here we have the different a sub n's. A sub 0 turns out to be the only non-zero value. We use almost the same command to figure out the b sub n's. So we simply change the a to b, change the cosine to sine, and don't forget, the b sub n's go from 1, not 0, and all the way through 5. Again, we type in the table command to show us what the b sub n's are. We press Shift-Enter to evaluate, and here are the values of the b sub n's. Now that we have the different a sub n's and b sub n's, we use Mathematica to define the Fourier approximation. We name this Fourier approx x. Again, we are defining a function, so we use the underscore. Instead of typing the individual terms, we'll use a summation here. So for the cosine terms, we have the sum of the a sub n's times the corresponding phi sub n, which is cosine n pi x over L. And the sum goes from n equals 0 through 5. Similarly, we have a summation for the sine terms. We have the sum of the b sub n's times sine of n pi x over L, n going from 1 through 5. We evaluate by pressing Shift-Enter, and we get the Fourier approximation. We check to see how good of an approximation the Fourier approximation is by plotting f of x together with the Fourier approximation. We use the built-in Mathematica command plot, and we start with an opening brace since we are plotting more than one function. We have f of x, and then the function Fourier approx x. Observe that we are not using the underscore here for the variable x, because we are not defining a function. We are using functions that we had already defined. Don't forget to close with a brace, and then x goes from minus L to L. Press Shift-Enter to evaluate, and here we have the graph of f and the Fourier approximation. The graph of f, of course, is the straight line tilted at 45 degrees, while the twisty curve is that of the Fourier approximation. We can say that the Fourier approximation has degree 5 because it goes all the way up to cosine 5 pi x over L and sine 5 pi x over L. This approximation is of degree 6, degree 7, 8, 9, and 10. The approximation is a decent approximation of f for the interval from minus L to L, L being equal to 1. The approximation, because it is made up of sine and cosine terms that are periodic, will also be periodic if extended beyond the interval. The graph of the Fourier approximation on the interval is like a rubber stamp that we repeatedly use at regular intervals to the left and to the right if we were to plot the Fourier approximation over the entire real line. The last part of the exercise asks us to determine the general formula for a sub n and b sub n. So we integrate f of x times cosine n pi x over L times w of x. Again, x going from minus L to L. And then we divide by the integral of cosine n pi x over L squared times w of x. and then x goes from minus L to L. Press Shift-Enter to evaluate. And here we have the general formula for the a sub n's. We should point out that this formula is applicable as long as n is not 0. The reason being the presence of n pi in the denominator. Even if we were to simplify this expression, which we leave as an exercise for the viewer, the resulting fraction will still be undefined at n equals 0. So as far as a sub 0 is concerned, we calculate the value of a sub 0 directly, using this formula. And we have already done that. Now, for n greater than or equal to 1, n pi will be an integer multiple of pi, so that sine of n pi is 0. The denominator in the formula, we should point out, will not be 0. Hence, a sub n is equal to 0 for n greater than or equal to 1. We had found this out for the values of a sub 1 through a sub 5 earlier in this exercise. We carry out a similar calculation for the b sub n's. We simply change cosine into sine and evaluate. For the b sub n's, n will be greater than or equal to 1. Sine n pi will still be 0. Now the angle n pi will have the same terminal side as 0 or 2 pi radians when n is even. As such, cosine n pi will be equal to 1. On the other hand, if n is odd, n pi will have its terminal side coincide with that of the angle pi, so that cosine n pi equals minus 1. One can shorten this to mean that cosine n pi is equal to negative 1 raised to the nth power. The factor n pi cancels out from both the numerator and the denominator. Therefore, b sub n is equal to minus 2 times negative 1 to the nth power divided by n pi. Or we can write this out as 2 times negative 1 raised to the n plus 1th power all over n pi.